Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. All right, welcome to the introduction to Chapter 9, Linear and Angular Velocities of a Rigid Body. Here we are. Short introduction. In this chapter, we study the motion of rigid bodies and therefore of robots, which are composed of rigid bodies. We aim to understand the notion of linear and angular velocity of a rigid body. Being able to model linear and angular velocities is a stepping stone to analyzing, simulating, and designing the motion of a rigid body. As in the previous chapter, and as illustrated in Figure 9.1, consider two general frames. Here is Figure 9.1. Sigma 0 is a fixed reference frame, fixed in space. It does not move at all. This frame is called the inertial reference frame, and Sigma 1 is fixed with the rigid body, and it is called the body frame. So you see Sigma 0 here, and you see Sigma 1 here in the figure. Moreover, we let P denote a general point possibly moving in space. We observe that this moving point satisfies the simple equation 9.1, where P0, the position 0, dot, that is the time derivative of the position of point P, is equal to V0 of t, where V0 is the linear velocity of the point P expressed with respect to frame sigma 0. Here's point P in the figure. Here we use the standard dot notation to denote the time derivative of P0. It is worth emphasizing that in equation 9.1, this equation above, both the point and its linear velocity are expressed with respect to a fixed frame sigma 0. Next, here are the questions we answer in this chapter. How do we describe the velocity of a rotating body or rotating frame? 2. What are linear and angular velocities of a moving rigid body? 3. What is the velocity of a time-varying rotation matrix R of t? 4. Assuming we understand a notion of angular velocity, in what frame is the angular velocity expressed? All right, we're going to look at those questions and more in the coming lectures. I'll see you then.